le plaisir aujourd'hui d'écouter Leonid Pastur pour sa deuxième conférence. Alors, depuis la semaine dernière, en fait, vous avez peut-être appris que le prix Nobel a été décerné sur des questions d'intrication. Et donc, cet exposé est vraiment dans le thème de ce qui a été récompensé. Donc, bon, je te donne la parole.
So, I'm about the toy model that very good illustration of the notions that we introduced and discussed last time. And this is a model which was proposed a long time ago. It is not written. It was a PG student by Hawking, Don Page. In 1993, proposed this simple model to describe the Hawking radiation from black hole, and the model is quite simple. You assume that it is the settings that we discussed. We view black hole and radiation as a composite system. Radiation is a system A, black hole is system B. Dimensions, everything is finite dimensional. Dimensions of these two systems written here. And then, since the whole system lives in the tensor product, the dimension of the state space of the system of black hole plus radiation is n, which is a product of the dimensions of these systems. And the proposal of Page was quite simple. He said that since we know nothing about black holes, in 1993 it was not so much known, at least theoretically, so we assume that the black hole in the state, it's like microcanonical ensemble statistically making, just a vector of the space. Since it is a tensor product, you index vectors by two indices. One runs for black hole, second for the radiation. And since we know nothing about the system, black hole in this case, we assume that this is a just random vector uniformly distributed over n-dimensional sphere. Yeah, I already, yes. Yeah, and this is all. It's like Gibbs in 1900, he introduced the microcanonical ensemble. He said that, okay, we know that energy is conserved, therefore the system has to live and the surface in the phase space of constant energy. And since we know nothing about a priori about the system, we assume that it is uniformly distributed over the isoenergetic surface. The same is here. And then, according to prescriptions that I gave last time, if you would like to learn something about quantum correlation between two subsystems, we have to consider we have to analyze entanglement entropy. To calculate the entanglement entropy, you have to know the reduced density matrix. So again, this is a pure state, and the net density matrix of pure states is a projection. It is written here. So the density matrix of the system, black hole plus radiation, is just, you see just rank one, the projection on the psi. And now, if we would like to have the density matrix, by the way, excuse me, it's a mistake. B shouldn't be here, because according to our notations, rho AB, it is the whole system. And if I trace out the degrees of freedom of B, being interested only in A, I have to sum over I have to make a partial trace with respect to the systems which I am not going to consider. So I have to sum over K. And now we have the reduced density matrix written like that. And these two vectors, I remind you, they are uniformly distributed over the sphere. And now we have to compute, so rho A is like here, so B has to be deleted. Yes, and we have to compute minus here again, excuse me, too many mistakes. Yes, and we have to calculate SA. And since our typical state is by definition random, so the reduced density matrix is also random, and the entanglement entropy is also random, and the simplest things to compute is just the expectation. So the Page computed for these dimensions 1, 2, 3, 4. It just made the conjecture that the general answer is like that. It was then confirmed by several calculations, which quite involved. And from that calculation, he was able, this is an exact formula, and since it's in fact this K is big, as always, because black hole is big, but radiation is not big. Page proposed this model as a model for the initial stage of the radiation, when after big, I don't know when it started, but quite long ago, and to see what is going on in the initial stage. So L is much less than K, and if we just assume that K is quite big, that means the limit, then the asymptotic formula is like that. So this is K is big, L is any, because this is exact formula. And let me remind you that if our density matrix would be just the unity, normalized by L, it is maximum value of entropy. Therefore, the leading term shows that our system, I mean radiation, is quite strongly correlated with the black hole, because it stays almost completely entanglement, and the unity, of course, is most entanglement already in the matrix. And so the conclusion was that on initial stage of radiation, the conclusion is more or less natural, but nevertheless it is obtained from completely simple, I would say, toy model. So we see that it is, in leading term, it is strongly correlated with black hole, the radiation, but there are certain corrections. So it is natural because, you know, the longer this process will continue, the more you have the coherence, you have processes that destroy quantum correlations. Therefore, there is a deficit, they call it deficit, this is second term. And so this was the result. But since we are dealing with random variables, so if you know nothing about the distribution, the expectation tells you almost nothing. Because, look, you have distribution which is not picked somewhere, so the expectation is, first moment, but generically to know the probability distribution, you have to have all the moments. Therefore, there were certain efforts to compute the fluctuations. They were computed, by the way, quite recently, I don't know, 3 or 4 years ago, more or less accurately. And the conclusion was, of course, that fluctuations vanish with K. Therefore, the expectation is representative. Nevertheless, the corresponding calculations, it is several papers, and I would like to present you a simple manifestation, if you want, the proof of this fact, by using certain results of random matrix theory. So let's go for that things. One more. So this is a conclusion that I already formulated. So if you are in a very early stage of the radiation process, you have leading terms that is almost completely entangled, and then you see the corrections. Yes, if you have if the radiation is a finite fraction of the black hole with respect to degrees of freedom, then you make double limit, keeping this ratio fixed, and it will give you, so it is logarithmically growing, but this is a constant. And there were some models that now allow to compute next terms, but it is another story. Let's keep on that simple setting. And now let me show you how it could be done by using random matrices quite fast and more efficient. So let's consider now the double index collection of random variables, all independent, identically distributed, normalized by the condition. They are complex. So the two moments are zero, but of course the normalization is that the expectation of absolute value squared is 1. Then now let's take a upper left corner of that double infinite matrix, and let's view. So let's view it just okay. You have this collection, yes, and apparently this is a vector of our space, because look, any vector indexed by two indices belong to this space, yes. And if you would like to compute its norm, the square of length, we have to compute this sum. And then, with these notations, now I view it as a matrix, rectangular matrix, K by L, and I follow the scheme by page, and I introduce my unit vector. Because of normalization, now it's vector over unit sphere, but it is uniformly distributed only if all these variables are Gaussian identically distributed. And that it is easy to show that if you have a Gaussian random variables of normalized, as I showed before, then this vector is uniformly distributed over the sphere. But in general, it could be not. So we have a bit general situation. Now I would like my density matrix, reduced density matrix will be like that. So I have that matrix rectangular times Hermitian conjugate. Now I have to divide for normalization by this sum. And let me not denote it a bit different. So I multiply both the numerator and denominator by k. And I introduce these two quantity. This is a random matrix, L by L, and this is just random variable, scalar random variable. And it's easy to find, just plug in this form, this one, into the definition of the entropy. So SA is just minus trace rho A log rho A. If you plug here, so what we will have? You will have WA over YA. Now log, I write log like that. This is a metric, this is a number, but nevertheless log, also you can also write log like for scalars. So here minus, excuse me. And then the first term will give you minus, the second term will be just everything. So it is a scalar. So we have this trace is 1 because of normalization. The leading term will be log YA minus, now you have 1 over YA, and now you have the trace WA log WA. You may remember that in my first lecture I explained it, just reminded. I believe that everybody knows what is the function of Hermitian operator. It is just the function of the operator, for example, log. It is just the matrix, the operator with the same eigen vectors, but eigenvalues are the functions of corresponding function. Yes. Now. And one more, if I introduce here density of states of W, so what is it? It is just 1 over L, the sum delta function of P minus P W minus W alpha. It is, yes, and the W alpha, the are eigenvalues of WA. This is Hermitian matrix, so if you introduce this function, you can write the second term in the form presented here. So this is exact formula And now what is going on? You can compute each term by using certain argument. So it is written what I have written already. So this is density of states, standard things for any remission operator, remission matrix. Now let's look first for the normalization, yes, for that thing, for Z. Let me write. Rho A is WA over YA, and YA is just 1 over K sum KL1 KL. Now, what do we have? We have the let's look at that expression. All xkl, they are independent and identically distributed. You have the certain amount, certain number of these summed eigenvalues divided on the number of terms. This is known quite well in everywhere, in probability and physics. This is the law of large numbers, or if you want, ergodic theorem, whatever. But we know that with probability 1, in that big space, this sum converges to the expectation. So there is this summing plays the role of expectation. It's typical ergodic situation. The mean over the phase is equal to mean over the ensemble. So we can write that it is for if K is big, L not necessarily, this sum is equal to the sum of expectation plus something that tends to 0, yes? Well, and then you can write in that form. Because our normalization, this is 1. So we see that sum behaves like, just K times L. And since Y is defined as in that way, so Y is asymptotically equal to, with probability 1, equal to L. So we have for the first term of our formula here, we have immediately have already log L, which was in the case of Page. And let me remind you that this the Page formula, this is in expectation. Myself, I have this leading term already with probability 1. That means all typical realizations, yes? Now let's deal with the second term, which is a bit more involved, of course. But as for leading term, we have already this. We see that leading term appears immediately. And I repeat in more general, slightly more general situation. So first, not necessarily Gaussian random variables. And second, it is not only for expectation, but for all typical realization. It is physics expression. In mathematicians, they would say that it's probability 1. Yes? Now let's pass to the second term. This is our matrix. So you see this is it is written here. And let's consider the two cases. You remember, on initial stage of the radiation, L is fixed. Black hole just started. Yes, so we keep L fixed, and K is big because K is the degrees of freedom of black hole, which is big. So we have, let's keep L fixed, but send K to infinity. Again, it is a law of large numbers. You have K terms divided by K, so it converges with probability 1 to the expectation. But expectation just delta symbol, so your matrix, all the matrix converges to 1. L-dimensional unity matrix, yes? And if you compute for matrix W equal 1, this sum, you'll find that it is 0, because you see log 1 is 0. So we see that on initial stage of the radiation, we have and for big black holes, we have the limit with probability 1 for typical realization, the same as in Page formula, but again, Page formula for the expectation. Yeah. And this is, we see that it is maximum entanglement still, the radiation, yes, for any collection. Let's go a bit further. Now, assume that okay, less early, but not completely early stage. We assumed, it was already discussed, that both numbers tends to infinity, but ratio tends to a non-zero number. And then, okay, now I have to use the result from random matrix theory, saying that you have this matrix, which was written here. And if now not only k, but L also tends to infinity proportionally, then the density of states converges to a nice expression which have the first term. You see, if lambda less than 1, you have a delta function at 0, and plus a smooth part. Okay, excuse me, please, but it is known now known as Marchenko-Pastur distribution. Yes, and if we put this expression to our integral, written here, so we see that this atom doesn't contribute because, again, log 1 is 0. And so only this part contributes. And if you compute accurately this integral, you'll find precisely the same expression. Therefore, we have proved that this process, which was somehow proposed, and description which was proposed by Page, is valid not only in the mean, which is not so much, but it is valid for typical realization. Now there are, since that time we have a lot of, almost 30 years, 20 years time, there was a lot of development, but somehow this simple toy, I would say toy model, triggered very nice and interesting direction of study. Now they are trying to justify the conjectures by Page, for example, about the almost uniform distribution by using string theory, a lot of things, quantum gravity, ADS, CDF corresponds, etc., semi-classical approximation, but this is a kind of guiding principle to indicate to which direction we have to move and how to follow. And Page itself, he proposed the process. He introduced explicitly the time, and he shows that if you describe, like that, so it will be time. So the process, the entanglement entropy will behave like that. So it will grow. So if process is developing, so radiation is developing, it gets more and more entanglement. And then when roughly half of this is called Page time, and it's called Page curve. Yeah, and then when black hole exhausted, and then of course everything decays. But it requires much more involved argument, but it's nice. This is why I have chosen this example to show that just from the very beginning, just after definitions that you get, you can find certain, reasonable result concerning quite complicated and serious physical object. Now it's end of the first part of roughly my lecture 1. Let me now pass to the lecture 2. Well, just a moment. And and I'll start just repeating a bit what Bernard said, that this week, why it doesn't work, I don't understand. This week he had a quite interesting scientific event. This was week for announcement of Nobel Prizes. In particular, the Nobel Prize in physics was given by these three colleagues of ours. and their names are written over. The first is Alana Spe, who was in. They are written. They are in. Settled in the alphabetical order, but historical order is different. The first person was John Clauser, who as early as 72, just several years after this Bell famous work on the Bell inequality, he was a PhD student. He communicated with Bell and made the first effort to measure, to verify this inequality of Bell. Unfortunately, I have no time to discuss, quite interesting subject, but nevertheless. And the first experiment is the very first experiment, but people recognized quite fast that there are certain loopholes, as say. So it's quite complicated logic to apply this inequality, so it was a bit simplified version in the experimental setting. Then next was Alana Spe, who found, you see, it was 10 years later, and it is from Paris, from France. He made much better experimental setting by using quite interesting tricks, and he measured the same subjects, the same same setting, and he confirmed the result by Clauser. And then again, now 16 years later, it was Anton Zellinger who not directly did this. He just proposed some things which is now known as quantum teleportation, which is based on the validity of Bell's inequalities. And so they were three pioneers, and they got the Nobel Prize, and it is written, just copied the citation from Nobel Committee. And they were pioneers, but even after all the three authors, there were certain still objections concerning the setting, interpretation, the Bell's inequality, and it was more or less completely set in 2015. Therefore, after the Zellinger, it was 17 years just to finish the story. So it was quite serious development, which was, by the way, motivated quite interesting experimental techniques, and now these Bell's inequalities are confirmed experimentally. It makes very serious foundation for the quantum information theory. Well, and I would like to say that Alana Spe is French, but I just would like to mention two more Nobel Prizes. One of the Cohen-Tanuji in 1998, it was about, and then in 2012 it was Serge Haroche. All of them, they were around this subject. So it was, I would say, and if we will mention even, Louis de Broglie, that we can say that France is in between the first quantum countries in the world. So it was quite nice, in my opinion. And I don't know whether, so these affiliations, they at time when they made their experiments. I know that Clauser now just is a consulting certain startup on quantum information theories that he just made this startup. Anton Zellinger now is in the University of Vienna, I believe. As for Alana Spe, maybe Bernard, you know better where is he? Is still in Paris Sud? Okay, so he's a professor here in Collège de France. No? No, okay. So anyway, this is a very nice event, and so it's nice to know. Well, let's go to, in fact, I had intention yesterday to prepare a short discussion of this, not Bell inequalities, but certain things that was at the beginning of all, but time is quite tight, so there is no time, unfortunately. Maybe next time I'll make a short version. So today we will discuss, so let me remind you. We started from the short reminder of basic facts of quantum mechanics, classical quantum mechanics, I mean, until 1935, and then after 1935, when the paper of Einstein, Rosen, Podolsky, and Schrödinger appeared, this, I would say, the second stage of quantum mechanics with very serious addition. And then we discussed this model in which, in which our bipartite system consists of two large pieces, because let me remind you, the both dimensions, K and L, we assume that they are big. Now I would like to consider the, so to say, elementary problem. We have just two qubits. Our system, SA, so it's a bit out of, so our system, bipartite system is two qubits, QA plus QB. Let me remind you that each qubit is just simplest possible quantum system, 2 by 2. You see the difference between quantum and classical mechanics. If you introduce non-commutativity, you have to have non-commutative object because these are observables in quantum mechanics. And this is one of the basic principles to deal with observables that do not commute. In two-dimensional space, we have already matrices that do not commute. Therefore, we have this. It is just to remind you what we are going. So we say that system unentangled if it is product, entangled it is not a product, it's state. If state is pure and if state is not pure, you have to assume that it is not the sum of these products, yes? And again, as I said, the qubit is the simplest possible quantum system. By the way, it appeared in the 60s in quantum optics because it's the simplest model of laser of two-level atoms. But in quantum information theory, we have this qubit, that means quantum bit, is as important as a bit in classical computer science. So it is a variable taking two values, 0 and 1, for example. Yes? What is our model? So entanglement entropy also we have already seen. It is just a reminder. Let me now, now we are coming to the important thing. So as I said, I am just a bit to justify what I am going to do. Let me just say that we are going to consider, as I wrote here, this very simple quantum system, just two qubits, and our state space is just tensor product of two-dimensional space. That means QA, QB. That means that our space is just 4 by 4, the four-dimensional Hilbert space in which the system lives. But it would be already also interesting because there are some things, but we are going to add to this, to introduce the certain elements, environment. So we assume that we have two qubits, for example, two spins or two-level atoms, but they are embedded in certain medium, like it happened always. So certain much bigger medium, which we call environment, yes? So, and we are going to consider what will happen. We are going to consider the dynamic of this system, but looking for just the reduced density matrix of these two things, and then to study the entanglement of this simple system. And as you remember, I explained in the first lecture that the simplest quantifier, that means the scalar quantities that characterize the entanglement, is entanglement entropy. But it turns out that the other also very interesting. The first of them, it's written here, called negativity. So it is a functional of the, we have again, still we have a bipartite system. And we have this density matrix, and it says that, okay, there is a quantity which characterizes the entanglement of two qubits between themselves, yes? So, and this quantity is like that. So you have your density matrix, which is indexed by 4 indices, like it should be in general, because I do not assume at the moment that dimension are 2. They could be any, yes? We have this density matrix. Then let's construct the things which is known as partial transpose. So you see, I transpose only the second indexes of the second system. So I pass from that matrix to partial transpose, where the pair of indexes related to the system B, subsystem B, is transposed. So you see the JB, KB, and here is opposite, yeah? And of course, it's easy to check that this matrix is also of trace 1, but not necessarily positive definite. And because of that, it is not, if it is not positive definite, it couldn't be density matrix of any quantum system. And this is very nice but simple observation. And so let's apply a bit of logic. So what it's the simple examples. So it's easy to check that if your matrix is a product, not entanglement, then this partial transpose matrix is always positive definite if it is a product. Therefore, by negation, we can derive immediately, as mathematicians used to say, a sufficient condition for your density matrix to be entanglement. It should be if it is if the matrix is this matrix is not positive definite, then rho is entanglement. So it's very convenient and simple criterion, because you just need to compute the spectrum of certain metrics. It's algebraic problem. Just your laptop easily can do it. So it's quite convenient criterion, and this is more or less arbitrary, but you have to quantify somehow this fact. But the simple quantification is here. So we introduce a quantity. It's called negativity. It is just the sum with minus of negative eigenvalues. So it measures to which extent, intuitively, your system, the more negative is your rho pt, the more entangled your system is just by intuition, by common sense. So this is called, I repeat, negativity, and it is okay. But in general, it's easy to show the simple examples. So if the dimension of your system is arbitrary, therefore it is just sufficient conditions. There are entanglement density metrics that do not satisfy this condition. But if you confine yourself on the matrix 2 by 2 or 2 by 3, there is a simple theorem saying that in that case it is 1-to-1. Therefore, if you deal with system with a bipartite system consisting of 2 qubits or qubit and the three-dimensional system, then it is necessary condition and it is necessary and sufficient condition. Well, there is another thing which is defined, unfortunately, much more complicated, but just to show you a bit. Yes, so it's called concurrence. But just to show you that there is certain quite non-trivial things to do. So let's introduce a quantity which is known as the entanglement of formation. It is introduced like that. For the pure state, it is just the entanglement entropy. Excuse me, I forgot the equality. Yes, and now, there is a quantum information theory interpretation. It is interpreted as a minimum number of Bell states, it's elementary entanglement states, which your big system could contain. if you have a mixed state, any density matrix could be written in that way. If psi's are orthogonal, it is just spectral theorem, but we assume that they are any, like what experiment will do you. Yes, so we have to write this thing, and then you have to minimize over all decomposition to purify, it's natural to minimize. But the minimization procedure is quite non-trivial, and it is not always algebraic. You have to make derivatives because you have to find the minimum, etc., etc. And so far, the solution of this minimization problem is known only for 2 qubits. And the formula is quite complicated. Let me show you. So if your system consists of 2 qubits, then this minimization procedure could be done. So it is of that form. Excuse me, the formula is quite complicated. H is a simple function. It's just a Shannon entropy of Bernoulli distribution. And so it is expressed, E expressed via C. And C is called concurrence. Also is quite complicated definition. I even do not bother you with a lot of explanation. I just would like to say that we are fortunate because for many interesting systems, including qubits, there are simple formulas for you can pass these serious things. And okay, if you look at the papers of last 10 years, you see that people already not thinking about entanglement of formation, just computing concurrence as itself. Yes, and I'll show you later simple formulas for certain classes of states where you can compute C. Well, and so we have how many quantifiers? We have a simple quantifier already familiar for us, entanglement entropy. We introduced negativity. We introduced the concurrence. And there is this fourth one, which is even more complicated, called quantum discord. I do not dare even to show you the definition, but intuition is very simple. You have a certain quantity known in classical information theory, which is called mutual information. It measures something interesting, and there is very nice interpretation of this mutual information in quantum case. But it turns out that because of general non-commutativity of observables, there are one simple classical definition has a 2 version because of non-commutativity. And their difference is discord by name. So it is, but it includes certain quite non-trivial optimization procedures. Therefore, I do not write it. But what is interesting in quantum correlation, because in quantum discord, because it measures not only entanglement, but it measures other correlations, because there are correlations that are not from entanglement, just from non-commutativity of your observables. And they are interested in certain situations, and I'll show on the pictures that there are cases when concurrence, for example, is 0. That means system is not entanglement, but nevertheless, Q is positive. That means that there are certain still quantum correlations, different from entanglement. Well, these are our, voltmeter and ampere meter and maybe ohm meter. We have at least 3 characteristics. Let's go now to the setting. What we are going to do? We are going to consider a certain, we are going to consider a certain system. What is going? Okay, excuse me. So certain system, in our case it will be just 2 qubits, but they are embedded in a big environment, yes? It's natural, common formula to write, how to write the Hamiltonian of this system, your system plus environment. Okay, this is a Hamiltonian of your system, Hamiltonian of your environment, and certain interaction between them. So it's quite general, yeah? And then we are going to study what is going on. You start from certain initial conditions. I'll show you them later. And then you switch on the dynamics by standard. I showed in the first lecture what is it's called the Liouville quantum Liouville equation. What is the equation for the, equation of motion for the density matrices. This is just the commutator of your Hamiltonian and your matrix. And of course, you have to add the initial condition here, and the formal solution of this equation is written here. So you have to consider now this this matrix, whose dimension is dimension of S times dimension of E. You have to now trace out the environment, because we are not interested to know what is going with the environment, at least on a certain stage. Yes, but we are interested in how does this environment influence the system. So we solve the dynamic equation, we trace out the environment degrees of freedom, and now we are going to calculate the entanglement quantifier that I showed the last time for the results that we obtain. Yeah. This is a scheme, general scheme. Now let's, being formulated in that form, it's quite general. It's not only about the qubits, I know, quantum information theory, etc. It is quite general, depending on how big your system are. Okay, if you look at the certain book on statistical mechanics, both quantum and classical, myself, I learned statistical mechanics from this Landau-Lifshitz, and there is a very nice derivation of the Gibbs distribution. So they said like that, okay, what is it? How to derive Gibbs distribution? We assume that we have our system already big enough, for example, the cubic centimeter of the matter, but embedded in much, much bigger in that room. We know that the whole system, our universe, in microcanonical state. We know nothing about. Therefore, the system, the states are uniformly distributed over the isoenergetic surface. Now, but we are not interested in the whole room. We are interested in the square cubic centimeter of the matter. It is now our experiment. So we trace out the degrees of freedom, and there are certain arguments showing that if you are interested in your system, which is big but not extremely big, you get, assuming the interaction of short range, you can arrive the Gibbs distribution from that scheme. Next part of the stage is so-called mesoscopic, now nanoscopic. In that case, your system is not so big already, but environment is still big. Quantum optics, laser, just one two-level system is your laser. So it was already good for dimension S, excuse me, the other one, 1, 2, 3. And nowadays, is quantum information theory. Unfortunately, we have to start from, for example, 2 qubits that I'm going to explain you now. Yes, but of course, eventually, we are interested again in big number of qubits, because if we believe that quantum computer could be ever built, yes, it could contain, as usual, supercomputers, they contain millions of bits. So quantum computers also should contain at least hundreds or thousands or even more bits. But as in classical mechanics, everybody has to start from two-body problem. So today we are about two-body problem of qubits. Yes, well, and so now system is quite simple. Okay, comparing with the general setting. So our system is 2 qubits, and their Hamiltonian is very simple. We assume that qubits themselves, they do not interact. So you see there is separation of variables. Yes, and the sigmas are as usually, these are Pauli matrices. Now, this is more or less, evident. But as for Hamiltonian of your environment interaction, there are many versions depending first of your interest and of course your abilities, what you can compute. Let me show you the simple picture. The most widely used scheme for the environment and the interaction, there are 3. First one, you assume that your 2 qubits are independent. That means every qubit has its own environment in its own interaction. So they're independent. And this problem is not just from the point of view of statistical mechanics, solid state theory, it is many-body. It's not interesting because they do not interact, two qubits. Where is the interest? Interest that we would like to know how does the initial condition influence. So we assume that initial condition is entanglement. Now we switch on the dynamic. We are trying to see what will happen. So it is the first thing. Second, even simpler, you assume that one of qubits is free. There is no environment, no interaction, just something which is called ancilla. But sometimes it is interesting, especially in quantum information science. And the third case is more realistic. You assume that qubits still do not interact, but they live in the same environment. So roughly speaking, these two cases, they are extreme cases of general situation. You have assume in reality, you have two spins embedded in the big environment, yes? If they are far enough from one another, you assume that they do not interact, you have the first scheme. If they are close enough, in that case, you assume the second scheme. And you see that the results are rather different in that two cases. Now, there is some amount by formulas, not necessarily to follow. But now I have written three Hamiltonian for three schemes. You see, the first scheme. So here they do not interact. The environment do not interact, and the interactions also. So the total Hamiltonian is here. You see, it is only the first system and only a second. So there is a separation of variables. So your dynamic is just, the density matrix will be a product because there is no cross terms. And the scheme 2, it is even simpler and most interesting in reaching the results is the scheme 3, where there is no interaction between environment, but you see, but it is the same environment for two spins, because here you have the two environments. Look, there are two J's, these are operators that determine the environment. You have two. Here is one for two. So they live, they embedded the same. Now the physical implementation is cubic. Now it's very interesting. It's called nitrogen impurities. You have in diamond, you introduce certain impurity. It turns out that you can control, etc. It's very good. So you have a piece of diamond, not big enough, of course, and just two impurity atoms. And depending on the distance between them, you use on the first and third scheme. Second is just for illustration. Yeah. Well, it is written once more what I said, that these two schemes seems not too interesting from our, mentality, which mostly on the many-body system. But it turns out it's also interesting. The most interesting case here, what is technically nice to start, because in that case, you can construct the dynamics very simple. It's just a product of dynamics of every spin, like ideal gas. Every particle moves by its own destiny. Well, and now about initial conditions, which plays an important role here. Most simple initial condition, you just assume again that two qubits are not entanglement. Second, they are entanglement because, this is, you see, these are written the expression for them, yes? These are basic vectors of your 4x4 system. And now we have a second condition. Okay, first it's pure condition. And here you have it's called generalized or Bell-like state. Bell proposed the states in which normalization factors are both, simplest possible, but you can write general things. So it is, our condition number 1 is already entanglement, strongly entanglement, because the Bell states, Bell proposed its own states to show that you can find entanglement in very, very simple situation. So it is elementary entanglement, I would say, yes. The second condition is just another Bell states. You see 0, 0, 1, 1, while here you have it's a bit more interesting. Yes, and the third one is called Werner, generalized Werner state. So you have a mixture of pure state, one of the two, and the complete entanglement state, because unity, as we already mentioned many times, the unit matrix is most entanglement density matrix. So you have a mixture. Depending on this parameter alpha 3, you'll have different situation. So let me just show you. You can, as a good exercise, to compute for which values of alpha 3 this state is entanglement or not. And you'll find, by using, for example, the concurrence that I showed before, you'll find that it is not entanglement. The system is not entanglement. This state is not entanglement if alpha is less than 1/3. So it's already in itself a bit interesting fact. After that, well, let me show you that if you see, we have this density matrix written symbolically. If you write them in the standard form of using a certain, you live in the tensor product. So your vectors are indexed by a pair, and your matrices by 4 indices. You can't write this matrix, but since you are in 4x4 space, you just redenote your basis vectors 1, 2, 3, 4. And if you do this, there are certain convenient way to redenote. And then, if you write all the density matrix that I have written, you see that they are block, despite they are of certain interest already, but it is somehow God helps us. So they are block matrices, therefore, it's what happened? So I remind you that the negativity, you just take your matrix, you do the partial transpose, and you compute eigenvalues. It's simple exercise because the matrix are block, and you'll find eigenvalues, and this is our expression for the negativity. You see directly via entries. So it's simple expression, algebraic, as we see. And it is no wonder, because it was clear from the very beginning. But more surprising that the concurrence is also easily to compute. So you see, you have this little c1 and little c2. They are expressed via entries of your density matrix, and you do this simple maximization procedure, you find C. So we know we have a nice expression for the entanglement quantifiers. We have our system. Now is the time to switch on the dynamics. You see what will happen. Well, let me show you first the case of one. We are going to study 2 qubits, but let's start from one body problem. Yes, okay, and it's quite widely accepted. It was motivated still quantum optics, so-called spin boson Hamiltonian. So you use as an environment just free quantum bosons, just oscillators. For example, it could be optic cavity with a light. Yes, and so your system is just one single spin, and you write interaction. You see sigma 1, sigma 3 to make no. Here is in fact, very simple story. It's product of sigma 1. If you just the coordinate of this boson field. It's quite simple thing, and it could be you can make the limit n to infinity. It means that your reservoir, your environment is microscopic already, and it can be shown that the result is completely determined by the you see this combination of coupling constants and the frequency of your spins. So you have a reduced density matrix which expressed via z. And nevertheless, it is quite complicated thing, and it's impossible to solve The Hamiltonian could be, okay, you can write a certain expression for dynamics by using, okay, Feynman integrals, etc., but it is not feasible. So people invented a lot of approximation, and one of the most used is so-called, Bogoliubov-Van Hove or Born-Markov is the following. If we are going to study large time, we take time big, but in general case it's hard. So we simultaneously we assume that interaction with the environment is weak, and this combination is fixed. So this tends to infinite time, interaction to zero, and this quantity is called slow time. And in classical case, this limit plus certain additional simple operation lead you to the Markov process, to kinetic equation, to standard things. In quantum case, it's more tricky, but nevertheless, it turns out that if you use this approximation as others, you'll find completely interesting phenomenon, which is written here. So you switch on the dynamic. I have written everything, Hamiltonians, everything, initial condition, but you use certain simple approximation of the dynamics, for example, like Z, and you find that your density, for example, your negativity, which is function of time, it becomes zero at a finite moment of time. For everybody who just heard something about non-equilibrium statistical mechanics, we know that if you switch on the dynamics and we let it to develop itself, there is a certain exponential decay to the equilibrium. Or at most, power law decay if your system is long range, etc. But never, I repeat, never, myself at least personally, never seen that your something that depends of time and characterize your system becomes zero at finite moment of time. This is why this dramatic term, entanglement, sudden death, but life is not absolutely pessimistic. There were a bit more complicated setting in which you kind of resurrection. After the death, there is certain period that your, for example, concurrence is zero, and then it appears again. So there is a kind of Jesus Christ situation. So it just, resurrection. It's called entanglement, sudden death. It was discovered first in very simple quantum optic situation by this, and there are other people. There were several discovered more or less simultaneously. I just mentioned this is a review in which it is more or less good explained. So we would like to describe this in certain. My goal is to show you how we will arrive to that situation. So let's start again from one qubit. Traditional approach, as I said, it is via spin boson, but it is complex situation. So let's, just to see something else, let's consider another case. I propose, instead of spin boson, I propose the Hamiltonian in which environment and the interaction is just one qubit with environment are not bosonic operator, but just random matrices. We know that random matrices now they're everywhere. People use them. They use them in many problems. Sometimes there is certain physical, arguments. Sometimes the argument is very simple. Okay, we do not know how to do concrete problem. Let's look for the typical problem. But typical problem is, by definition, is a random problem. So let's assume that our operator, quantum mechanical operator that describes environment and the interaction is random. And we need to assume two things. First, that this matrix, if you write its density of states, and I'm going, of course, to make n big, because I would like to have the environment much bigger than my system, yes, and we assume that the density of states of this matrix, Hamiltonian of environment, it has nice limit, which is continuous. Yes, and it is, by the way, the analog, as I said, of that function which appears in spin boson. Yeah. So nothing else I need from environment. It is good because environment is anything. Yes. Now, as for interaction, I would like to be a bit more specific. I would assume that environment is random, so it is a Hermitian matrix, and modular hermeticity, its entries are independent. So they are all independent, normalized like that. We have seen already this normalization, yes? The expectation of this and that is 0, and the expectation of that is 1 over n to have a nice limit, yeah? Okay, this is known, by the way, maybe it's now everywhere. If you have assumed that these W's are Gaussian, then we have the random matrix, which is called random unitary ensemble, and GUE, okay, it's almost on the affiche. Yes, and now, so it is my model. And now I have to, just to start dynamics, I need one more thing, yeah? So random matrices, it's already, as I said, it is used for describe very many things, especially, you see, standard Hamiltonian, it's short range. So what does it mean? That the entries of your Hamiltonian written as a matrix in a good enough basis, roughly speaking, they decay the farther you from principal diagonal, the they decay in that direction. So in that direction, they are more or less the same. It's short range. But in random matrix, all the entries are of the same order of magnitude. And this is a kind of situation, by the way, which is I even dare to write. I have seen recently in Nature the tomogram of human brain, and there are neurons, and they're everywhere. So it's quite dense network. And as for physics sides, we know that this situation when we have long-range interactions, Mean field, which is one of the principal approximation in statistical mechanics. So it seems more or less natural. And now about the initial condition, we assume that at finite moment, your environment in your system, 2 qubits, they are not entangled. Okay, we can always prepare, and there is certain procedure in quantum mechanics saying that it is always possible. If you do not mind what is the dimension of P, you always can write in that form. It's called entanglement purification. Yeah. So, but and rho by rho is just for one qubit just arbitrary 2 by 2 matrix. Yes. So now we write the equation. We do we switch on the dynamic. And what is their goal? What we have to study? Since again my Hamiltonian is random, reduced density matrix is random, and the entanglement quantifiers are random. So what we have to compute? Of course, we have to start from expectation, but to be sure that we get certain reasonable information to believe, we assume we have to check the fluctuations. We have to show that your genuine, your random reduced density matrix almost doesn't fluctuate. So it is more or less, then it is represented by mean. And as a first step, it is possible, it is standard tricks in random matrix here. You have to show that the variance, and what is the variance? Let me remind you. If you have a random variable, psi, the first things to compute, as we already discussed, is expectation. It's real. I assume at the moment it is real, yes? Then I compute the expectation, and then the variance of my xi is the deviation of or maybe it's better to write in the form. So it is just how much your typical values, they are different from the expectation. This is variance if it tends to 0. With respect to certain parameter, we say okay, in mathematics, they say that it is not random practically. Physicists will say that your quantity psi, some physical quantity characteristic, is self-averaging. Yes, and we have to check first this property. This could be done by using the technique of random matrix theory. I have no time, unfortunately, to present, but nevertheless, the result is quite simple. You see, okay, there is time. Of course, for big time, it's not good enough, but if it is not too big, it's good, because, you have n in the denominator. So your fluctuations, at least in that part of the parameters, are small. And we know in non-equilibrium mechanics that there is a problem with time. You can't make time too big, because then there is no ergodicity, there are many problems, so that your time is usually much less than, than certain microscopic quantities, much bigger. Yeah, so what? And here is the case. And now, by using, provided that it is done, we can confine themselves to only for the expectation. Expectation could be computed. So you make limit n to infinity, keeping t fixed still in V, not 0, just something, yes? And you find the following, that the limit in reduced density matrix, solve certain self-consistent equations, a bit similar to the Curie waves, so self-consistent equations. Now, you can follow the dynamics, and you see the dynamics is not Markovian. So Markovian dynamics is, what does it mean? It is simply in time nearest neighbors. So your objects that evolve according to Markovian dynamics feels on the nearest past. Not Markovian, that means that it is the time correlations are more strong, yeah? So we can show you that it is not Markovian, but in quantum mechanics, this is not classical Markov process. This quantum Markov process, in quantum Markov process, corresponding equation is not Fokker-Planck, but it's known as a quantum Fokker-Planck. It was introduced by Lindblad. Yeah. Moreover, so it is not Markovian, like in classical case. Moreover, if you compute the infinite time your density matrix, you'll see that it depends on initial condition. It is just blasphemy with respect to our intuition, which is grew up on the philosophy of non-equilibrium statistical mechanics. We used to think that if you leave system to evolve long enough, it will converge to equilibrium, which doesn't depend on the initial conditions. Otherwise, it's completely strange story. But here it happens. So you have, in what is interpretation? It is interpretation that random matrices, in spin boson, it could be done. You have this property of equilibrium. It means that your random matrix environment, it is big, but not big enough. So somehow it is not macroscopic environment, but mesoscopic. And it is okay. It's bad and good depending on what you would like to have. Yes? Well, but nevertheless, the formula is quite involved. If I would write them, it would be 2 slides. Therefore, the next step, let's do this Bogoliubov-Van Hove limit. And then we arrive to very simple formulas for the diagonal entries. Off-diagonal is a bit different, but let's concentrate. So this is just exact expression in that limit. Interaction to 0, time to infinity, product is fixed. So you see, this is what I said. You have terms that do not depend on time. You have terms that exponentially decay. If your tau is big, these are vanish, but you have still this expression. It is not equilibrium. Moreover, it is not Gibbs. Moreover, it fills initial conditions. And we just analyzed this formula, and we found that it is Gibbs only in trivial situation when you see what is gamma. Gamma is this expression, so it is just density of states, and it is known since early 30s it was introduced by Fermi, who considered first the time evolution in quantum systems. So it's called Fermi golden rule. So your relaxation time, which is inverse gamma, is expressed via density of states of your system. So its formula is a bit similar to classical one, is with respect to golden rule, etc. But on the other hand, it is different because your tau infinity formula is not Gibbs. And moreover, it is not Markov process except very simple situation. So it's quite rich. And then let's pass for 2 qubits. Oh, you use all these Hamiltonian, do not look for them too much because, okay, they are complex, but it is just the same idea. You write 2 qubits version of the Hamiltonian that I have written before. Yes, and then you switch on again the dynamics. It's, again, could be found, but it's horrible formulas containing contour intervals, etc., etc. So we again confine ourselves to the, formula quite complicated, and nevertheless, you start from simple things because, as I said before, the first 2 dynamics, when your spins are independent or independent in with ancilla, then your density matrix could be written like that. So it is 4×4 matrix, but it is, so it, let me write 2 because for 2 qubits, it will be some, you have first 1 qubit, and your dynamic will be rho 1 on T. Yes? So you obtain the rho 1 on T, you apply a certain operator depending on your system, A, for example, A. It's super operator which acts on rho A naught. So it is just an operator of evolution, yes? And it turns out that when your dynamics are independent, your phi A B is just the product phi A, because you have a separation of variables. But therefore, the result is here like that, phi A times applied for a naught, which is not factorized in general, only for 0. So everything, all the entanglement comes not from the, dynamics, but from initial conditions. Yes, it is for cases Y and F. The third case, when you have a common environment for the both spins, the dynamics is not factorized, and in the first 2 cases, I can use just the formulas that I have written before, but in that case, you have to work in U, and the situation is not simple, so we take as a density of states very simple formula, so-called Lorentz distribution. These are for physicists, mathematicians call it Cauchy distribution. Yes, and okay, you use these things, you after that you compute the formulas, and then you use again Bogolyubov and Hall, and then you compute the concurrence and the negativity, and there is a notation which I have to explain. So let me remind you, you have 3 models: independent, free, and common. And you have 4 initial conditions. So you write the model like model, equal M. So M is for Hamiltonian, little m for initial conditions. And now let us see. So this is a simple case, you see either free or independent. This is a concurrence, and this is a negativity. You see, it is zero at finite moment. So you have, even already on simple dynamics, when dynamic factorize, and the whole entanglement comes only through initial conditions, you have already this phenomenon, the entanglement sudden death. And it's, of course, interesting. I can't explain intuitively why they are zero simultaneously. But nevertheless, so it means that it needs some phenomenon, not just because of choice of your measuring apparatus. So we have, they are a bit different, coming in the middle part of time, but at the beginning we took them, all of them is one, nothing is okay. And now we see that they are zero at finite moment, but it might depend on the situation. Let me show what, this is independent, this is free. So you see free, it is just one, your qubit is just free, okay, no interaction, no environment, and it lives a bit longer. As for when your initial condition is strongly entanglement, then it lives a bit shorter. You have zero. And I am surprised that our model is quite simple, okay, in primitive if you want, but there is experimental results obtained before our work on that. They show quite similar behavior. It was from light by using photons. It's most widely used object. These are quantum optics to model phenomenon related to entanglement. So, okay, it's reasonable, good. Okay, it was a surprise, but pleasant surprise. Now, a more complex situation. You have already the model C. C is common. So the model C, it is a common. So you have now your, if you see the Hamiltonian, so you see no complex explicit interaction between qubits, but every qubit interacts with environment with the same, and via that environment there is effective interaction between them. And this is because you have much more developed picture. You see, this is a concurrent, this is a negative. It turns out that concurrence in many cases equals to two negativities, and you have the model C, common reservoir, and its second boundary initial condition is just Bell states. And you see, there is a death, they die. Okay, depending on parameters, the death is different. But we are fortunate, they birth, there is a resurrection. So you see, they are again non-zero. There is just an interval, they are death, when they are dead. And then again, they are alive. And this picture is just in vertical direction. We just made scale bigger just to see what is going on. So you see this thing here is just like that and pressed in tau, and you see that this is the initial stage. It is here. So they are growing. Then there is a maximum. They are decaying. Some of them they are dead at finite moment, but some of them still alive. So you have a quite different behavior. Yes? And depending on parameters, you see many things. Yes? And the next slide is it's more, if you want. So you see, this is a condition 0, when at initial moment there is no entanglement. So your initial conditions correspond to two qubits that are not entanglement, unlike previous case, yes? And you see, of course, because of that, at the initial moment, there is no entanglement. You start to evolve, there is no entanglement, but since they qubits interact via common environment, they feel one another, and eventually there is entanglement, and there's, different cases. In that case, there is so they are dead here, there is a birth here, and then they are dead again. Here you have a bit different situation. They lived longer. And this is this is interesting story because this is condition 0, they are completely unentangled. Condition 3, they are partially entangled. And you see, again, there is a certain diversity of possible, behavior. This part is similar to that part, and this part similar to that, but unlike that, there is an intermediate short death, etc. You see, you have a certain, there is a lot of times when you have the death, birth, death, etc. Yes, and now let's, so to show you that there could be many births, not just once. You have a lot, yes? So depending on your, on the choice of your parameters, you see that, there is, how much? 1, 2, 3, 4 deaths and 1 in 4 births, rebirths. And again, depending on parameters, you can, it behave like that or just once. Yes, and here, okay, a lot. You have a zoo possible situation, you see. There is a monotone part, there is non-monotone part, there are deaths, births, etc., etc. So there is quite a lot of version of behavior, and the next goal is to sort out them and to understand what could be interpretation of that thing. But even in two-body problem in classical mechanics, we have a lot of interesting things happening. So no wonder, in fact, yes? And now let me show you discord. As I said, the discord is more complex quantity, and it feels not only entanglement, but mostly different correlations as entanglement. So we see that it could decay, but it could even grow, either monotonically or certain conditions. So depending on the model and parameters, and there is only one case when it dies, but exponentially, not in the finite moment, exponentially dies if you have a certain tuning of parameters written here. So you have an enormous amount of behavior. And last slide to show you, again, discord. It's more, it's three-dimensional roughly picture. You have a lot of behavior. And there is one more thing. Discord is too complicated. People invented a simpler quantity, which is called geometric discord, which is simpler to calculate. And you see, again, a lot of possibility to behave. Well, thank you very much.